Alrighty then. Well, thing says we're live, so we must be alive. Hey guys, what's going on? Memes here. And today we're going to be doing something a little bit different because earlier today I was having a quick discussion with Thad. I was showing him a video from a Dr. Unzicker who's actually going to be at Demysticon 2025, put on by the Demystify Sci Crew. Shout out to Anastasia and Shiloh. And Dr. Unzicker was presenting a very interesting coincidence between some aspects of the proton and Planck's constant. So let's actually just jump right into it right now. So we'll share the tab with the class. And link is in the doobly-doo, of course, if you want to go check out the full video. And it's titled The Proton Radius Riddle and an Intriguing Coincidence. So since we all know I'm a big fan of coinkydinks, let's take a look at what the good doctor is talking about.
So, but this is, as I said, also a sideline. I want to focus today on something really interesting from a fundamental point of view. And there is a coincidence. And this is very interesting. It has been noted by a couple of heterodox scientists, interestingly. And I mean, two things to mention here. Why did I insert this p/2? Because it's fairly precise now. You can argue about this is coincidence, and I don't believe in numerology. Okay. But nonetheless,
just a quick update. Shout out and swift recoveries to Rick DeWitt, a Fractal faculty member. But I believe he had mentioned the other day in some correspondence that I believe Tim Maudlin had coined the term nomenology. Now, what is that? I'm not exactly sure. Perhaps it's numerology that may actually be useful. So let us continue.
In any case, it remains remarkable that we have an order of magnitude coincidence of h, Planck's constant, with c, the mass of the proton, and the radius of the proton. And this is important because the proton is the only particle for which such a relation holds. And if you think about the plethora of particles in modern physics, I mean, that kind of gives the proton a special importance. And by the way, it's the only stable massive particle we have. So let's think about these fundamental things.
To be fair, I mean, the electron is stable, but it's also like 1,836 times smaller. So as far as mass goes, that seems to hold until we smash them together near close to the speed of light. Yes.
Anyway, the reason why I made this video is because indeed the numerical coincidence is quite close if you put the factor p/2 in here. And I have covered this also in another video, but I want to give it still another twist today. So let's look at it and do a little bit of calculations. Let's play with these numbers.
Okay, so long story short is if you take basically, we can just go back. So basically this number over here. All right, so basically if you take pi divided by 2, all right, so that's our dimensionless factor there. See, the speed of light, the mass of the proton, and the radius of the proton, you get out about 3 significant digits accuracy with Planck's constant and the correct magnitude within the dimensions. So since Planck's constant is it's units of action, or you could say elementary viscosity, but basically it's the unit of action. If you've ever heard the term the principle of least action, okay, maybe it's not necessarily the exact same thing, but it's basically at least what Max Planck happened to use to help at least seemingly solve the ultraviolet catastrophe. Basically, when you're looking at the classical ultraviolet distribution, eventually it's, oh my God, it's going up to infinity. But if we were to quantize, quanta, so to speak, then basically the problem kind of goes away. So you have this right here. So that's, if you want to watch the rest of it, you can feel free to go on. He goes on to some other things. And while I might not agree with a good doctor on everything, then again, I don't agree with everything with anybody. So even myself at times. So let's let's go to precisely what that would give us. So let's just bring it up here. Our good friend Wolfram Alpha. And we're going to pop over here. Okay. So if we go to Wolfram Alpha, we'll take that expression there. So we take that pi divided by 2. And we do c for the speed of light. And then we do the proton mass. And then the proton radius. Okay. We throw that all in there. Okay. So we get this thingy right here. So input interpretation. As you can see, we have pi divided by 2, c the speed of light, the mass of the proton, and then the default proton root mean square charge radius, aka the charge radius of the proton. Okay. So as we can see, it gives us pretty dang good agreement with Planck's constant. And since Planck's reduced constant is basically just that divided by a factor of 2 pi. 2 pi is basically 6.28. This is 6.3. So it's got roughly about 3 significant digits accuracy with Planck's with Planck's constant itself. So that's very interesting. As you can see, it's action, angular momentum there, whatever that means. Okay. So I was showing Thad this earlier, and I had played around a little bit before, and basically after showing Thad, it's such a simple expression, I had to play and do some slight manipulation and everything, and mostly just because of the power of Wolfram Alpha. Thank you, Team Wolfram. It helps make calculations a lot easier, at least for your initial first level calculation. Again, you're going to want to go in and put other things there, but for at least a first level initial dive, does a pretty dang good job. All right. So as we can see here, but Wolfram Alpha gives us options. Oh. The classical proton radius, that's an option? Let's click it. Okay. So we click it. And then what we're going to do, okay, you get this here. I'm like, all right, I'm not really sure what to make of that, but let's take off the dimensionless term and just look at the dimension full terms here. Because remember, c, the speed of light, we got to let it know it's the unit. And we got to let it know we're using the classical radius. And since I'm listing a bunch of seemingly arbitrary things that may not be so arbitrary, we're going to click multiplication. Okay. So now we have c, which is a length divided by a time. We've got a mass, so that will give us length, mass, time, and then we've got a radius, so that's another length. So now we've got 2 lengths of mass divided by time. Well, that equals action because it's mass, area, rate. So we get a mass, a length squared, which is area, divided by time. So that's a rate there. Cool. Now, the whole reason I'm showing you this isn't just because, oh, blah, blah, blah. Okay. It's because of what Wolfram Alpha then tells us. So if we look here, okay, we go through here. Now, is there anything that might stand out here? Okay. Now, first, that 7.69 times 10 to the minus 37, blah, blah, that doesn't mean a dang thing to me. Okay, neither does this, neither does this. This doesn't mean a thing. Wait. 1 over 137 reduced Planck's constant, aka hbar. Now that's interesting. Okay, now for those of you that have been following and or may know a little bit of the greater pop culture stuff within science and stuff, you may have heard the whole mystery of 1 over 137. Okay, why? Because that approximates the fine structure constant, aka alpha. So, of course, I had to do just the standard thing. What happens if I take this whole thing and we divide it by the fine structure constant? Okay. We put that in, and now we're going to have to validate these all other things. So again, it's going with the most likely terms there. So we're using the classical radius. We're doing multiplication. Okay. So what do we got now? We got the speed of light times the proton mass times the classical proton radius divided by alpha, the fine structure constant. What do we get? Now, for those of you that have gone down Wolfram holes, some of these numbers might look quite familiar. Why? It's got approximately 9-digit agreement with h bar, Planck's reduced constant. Don't that just beat all? As we can see, we're in the right dimension. I did not expect this at all. I just figured, listen, when you go down a bunch of Wolfram holes and you're just going to be doing numerology, nomenology, whatever the heck you want to call it, most routes you go down are dead ends. As soon as I saw that 1 over 137, I'm like, no, that's got to be estimating. And then we went from about 3 significant digits of accuracy to 9. H bar is defined at 10. So maybe there's a little bit of some wonkiness going on at the end there, but I just found it interesting that we seem to be able to triple the number of digits of agreement by doing this one little trick. Swapping out the charge radius of the proton with the classical radius. So that was very interesting to me. Hey, welcome, Poindexter. Good to see you, my friend. Yes, for all of those that may be joining now or temporally in the future, I think this is quite fascinating. And again, I haven't done the full deep dive into all this and that and everything, just because, this is just... Again, I was not expecting this, and again, this wasn't me. I was just playing around. If anything, I'm basically a monkey with a magical typewriter and an idea of where to look. Why? Because Thad taught me it's like, well, every once in a while you entertain an idea. If you see an interesting expression, especially if it's simple, because as Vanessa from the monastery has said, nature is simple, perhaps we can actually figure out something or see what's going on here. And at first I was looking at this and I just thought, I'm like, okay, maybe it's just like the classical radius of the electron and the Bohr radius because that has a difference of the fine structure constant. But when you divide the proton radius by our classical radius, its difference is like 540 or 550. And I'm like, what's the square root of that? It's like 23.9. So I'm like, Okay. My initial thought was, it's just a trivial standard 1 over 137 thing. And I'm like, that seems to get us very good agreement with H bar. So, it's maybe something that Dr. Unzicker may be interested in. Maybe some other folks would be interested in this. I don't know. Maybe this has been covered a bunch of other places. Maybe people know about this because I'm just a dude on the internet. It's like human beings, I haven't read the old internet. Maybe ChatGPT has read some of the internet back and forth and everything, but to be fair, I haven't really looked that much. I just got really excited, so I'm like, all right, so let's change our topics from whatever I was planning on talking about, which I didn't really have anything planned because we just figure out stuff as we go, and we happen to get there. So I'm like, that is quite interesting. So let's play around a little bit. So let's see. So let's go to let's make another tab over here. So let's just check out what's going on. Poindexter's asking, when I think of spinners, I bet there are synergies within quantum space. Well, that's interesting because I think the way Thad is laying out the new book and everything is, okay, if we're going to say that the hyperbolic figure 8 knots complement, it kind of seems like a bispinner. Why? Because it's got 2 minimal 3 manifolds that are connecting that seem to be going in slightly different directions, doing a particular articulation, and then again the whole Dirac equation, as far as my understanding, it's relating 4 things to basically H bar and whatnot. So you basically have, I believe they call them 4 component spinners with the Dirac equation. Physics Explained, great channel on YouTube, actually recently put out a video about this because I was actually thinking, now that you bring that up, I was thinking about that the other day, and then all of a sudden I go back to YouTube, I hit the little refresh thing, and I'm like, oh, physics explained literally is going through the Dirac equation. And I'm like, oh, I was literally just thinking about the Dirac equation. Yes, said nobody ever until maybe now. So, so let's actually do this. Hold on. Let's do, just so, maybe I just got this all wrong, but the proton radius divided by the proton classical proton radius. Okay. Let's see. Okay. So, okay, proton root mean square charge radius, so the standard radius it inputs, divided per classical proton radius. Okay. 550. That's not 137. Let's try it. Let's try it the other way. What's it gonna give us? Maybe this will explain why. Okay, about that. Again, if we multiply that by like 3, maybe we get the fine structure constant, maybe 4. Do we need 4? It's going to be about 4, I think. Okay. So apparently, if we put a factor of 4 there, for the classical proton radius to the square charge radius, okay, not 7, 3. Okay, so that's about an approximation because the fine structure constant is 0.00729. So, oh, I didn't know that before. Why is it 4? I don't know, because it's the root mean charge square radius. Is it? It can't possibly be something to do kind of like there's a box there with 4 squares. Again, that's an extreme oversimplification for what might be going on. But the calculation is just, you're going from about 3 significant digits up to 9. I'm like, I was not expecting that at all. So, again, maybe this is something that a bunch of folks have known for a while or everything. Because my initial thought was one of the ways that you get the Compton wavelength for things is you just take Planck's constant. So you just take Planck's constant. Planck's constant. So not the reduced one, just the full one. And then you enter a mass here. So we can do like the proton mass, because Wolfram alpha, we can just use natural language, and then you multiply it by the speed of light, c. Okay. And that will give us basically the range of the strong nuclear force, and basically the proton's Compton wavelength there. Okay. So that's how you do the Compton wavelength for things. Basically, you just have Planck's constant, and then you divide it by whatever mass you want to put in, multiply it by c. So like if we did the Planck mass here, we're going to get, what is it, Planck length or 2 pi Planck length? Yeah, 2 pi Planck lengths there. Okay. Because, well, if you're going to do a wavelength, well, if the Planck length is the minimum of length, and you got to do it 2 pi because we need a sinusoidal wave, it's going to be 2 pi Planck length, aka the length of a string in M theory. So it was just one of those things where it's like, I was not expecting that. It's like, oh, we just change one thing, swap the dimensionless pi over 2 term with 1 over alpha, and we extend our significant digits by like three times. I thought that was pretty cool. So, hey, Dr. Smith, thank you for joining. We're just going over Dr. Unzicker, what calculation that I said it showed recently. So, recently is technically in the past year. I went back, and it's like 7 months ago. So, what is it? Okay. So let's. Shall we go back to the video? Let's listen to Dr. Unzicker a little bit more. We can see what else he has to say about this. So basically, he's actually doing the math out there and everything. So let us continue.
So first of all, again, you have, if you put it in here, the numerical value of Planck's constant, the speed of light by definition, the mass of the proton, a couple of digits, and you end up with this fairly precise value. And I think it is kind of remarkable that you have these 2-3 digits of precision. Anyhow, if we now think about the coincidence and try to play around, what can we do? You can obviously multiply with C. And then what you can also do, you have HC at the left-hand side, and HC can be...
I'm realizing that I muted myself. I was listening to the good doctor. All right, so he's so close. He's already playing around with alpha right there, but it's just, he has that pi over 2 there. And again, all we did was literally swap out the proton's charge radius, or the traditional, or whatever we have for the standard radius, with its classical radius. And it gets about 9 significant digits of agreement. It's like about 8.5, because Wolfram Alpha rounds. So let's go back here so we can show the other good doctor what is going on. So we go back to our window here. Boom, boom, boom. Share. Okay, so let's go back a little bit. Okay. So first things first. Here's Dr. Unzicker's initial calculation. So we have basically pi divided by 2, because, all right, we're kind of quartering up a circle, because pi is half a circle, all right, times the speed of light, times the proton mass, times the, oh, hold on, we need to change it, okay. Because if we're using this radius, the proton root mean square charge radius, whatever that is, it's approximately the magnitude of Planck's constant, so it at least gets the first 2 to 3-ish significant digits. And since the reduced Planck's constant is 2 pi, if that was 6.28, it's pretty close. So all we did was literally just did this. So it's like, all right, so let's just take off that pi over 2 term, and let's see exactly what that is. What do we got? Oh, it's giving us, yes, because people always put these series of digits in. So we're going to assume C, rather than being a particle, is a unit, aka the speed of light. Okay, root mean charge, rather than list, we want multiplication. All right. So as we can see here, yeah. Oh. That's interesting. Oh, so it literally is a 4 factor there. Oh, I guess that's where that comes from. Oh. That's very cool. Okay, see, we're learning. People just even asking questions is huge. So, okay, so what did I do wrong here? I feel like I did something wrong because this was different. Oh, we're using the root mean charge radius. Okay, so that's an answer to that. So we could actually, let's just divide this whole dang thing by 4. Okay, so it's approximately giving us Planck's reduced constant. So okay, so we got about the same accuracy there. Let's actually let's encase these, just so we have our protective brackets, because it's better to have them and not need them than need them and not have them. Hey, welcome, K-Shaw. I saw you over at Tony's stream a little bit earlier. Sorry, I was doing some other stuff and things. Don't always have the ability to say hi, so I'm saying hi now. All right, so let's go back. So all right, so let's go right back there. Let's take off that 4, and let's change it to the classical radius of the proton. All right. Okay. Yep. We gotta make sure we're putting in the right thingies there. That multiplication. Okay. Back to the classical proton radius. All right. So again, I get a bunch of numbers. Don't worry. I have no idea what those numbers are. These things don't mean a thing to me. Comparison, that doesn't mean a thing to me. This means a thing to me. As soon as I look at this, it's like, wait a second, hold on. So what you're saying is, if we literally just drop that pi divided by 2 term that Dr. Unzicker had postulated, and we literally do this one trick and swap the proton's charge radius with its classical radius, the difference between this expression and Planck's reduced constant, aka h bar, the elementary unit action, is about 1 over 137. Imagine my shock. So then the next obvious thing to do is, I mean, you could divide by 137, but we want a little bit more precision. So since, again, Wolfram Alpha, the magic of it, just use natural language, type in fine, structure, constant. All right, and we need multiplication, and we want its classical radius. And lucky, oh, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's usually, I think it's about 1, 7 for the last 2 digits there, so it's rounding up there. Oh, this appears to be about 9 significant digits of accuracy with h bar. A thing that basically we use to make quantum mechanics work. Huh. That's interesting. Hey, welcome, Kali. Good to see you, good to see you. I'm liking some of those animation videos you got. All right, and Kali is postulating that spinors and CPI violation, in her opinion, is an artifact of compact time. I'm still trying to work through that. I mean, that sounds like it could kind of be right. I mean, again, I'm a simple type of dude. I'm just thinking, I'm like, well, if the universe as we know it had a preferred direction of, I don't know, maybe angular momentum, let's say, because, I don't know, we're messing around with angular momentum, that maybe that could explain some of the perhaps handedness, or at least observed handedness, and maybe that's kind of what you're saying there. Again, I don't want to put words in your mouth. I'm just kind of conjecturing because, oh, hold on. We need Professor Wolfram. We need to make ourselves legit. So let's cover our butts here. All right, buckle up, everybody, because...
Although this is going to be weird, and it's going to be about a different...
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might be just hyper-rurial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rurial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Full disclosure, this is a MacBook Pro. We want to be as open and transparent as much as we can, right? So, all right, I digress. Okay. I'm actually not really sure what else to say. I mean, this is all I don't know what to, again, I'm not a particle physicist, so I'm not really sure what to do with this. It's just the doctor was presenting an interesting coincidence because it happened to get the correct magnitude, right dimensions, as well as first several digits of Planck's constant, so being the Wolfram sycophant I am, and also a gamer that happens to like to search lots of nooks and crannies for potential treasure and often finding things that aren't really useful, going down dead end after dead end after dead end. Every once in a while, if you find something, you're like, oh, this is very shiny. Is this gold? I don't know. Maybe it's fool's gold. This could just be fool's gold. Maybe there's absolutely nothing to this. But all I know is, okay, I just swap pi divided by 2 for 1 over the fine structure constant, and we just changed the proton from its charge radius to its classical radius, and we tripled the significant digits of accuracy. Why? I don't know. Hey, listen, this is just a calculation. I'm sure there's a bunch of smart folks, much smarter than me, that could try to explain why this is the case. I also haven't done my due diligence to just kind of look to see what's going on. It's, I kind of noticed this. Okay, maybe reach out to maybe some few folks that are interested. It kind of showed that. It's like, I was like, I don't think I've seen this anyplace. So hold on, let's try this. I should probably actually go to the sources and stuff, but before it got too late, I just wanted to do a quick live stream, and also because I can also clip out some of this to do a video, which I felt would be more interesting, and also anytime if you happen to use the picture and name of another YouTuber, especially if they're larger than you. I don't know. Is this how we get clout and stuff? But, oh, Gabriel. Good to see you, my friend. Let's see. Gabriel is saying, hello, memes. I've seen Sandro Guerrero. Yeah, I've seen Sandro before. Thermodynamics may seem crazy, but here's the thing. Gabriel, if there's one thing that I've learned, you never know where a good idea comes from. And sometimes, perhaps, it's not a question of whether somebody is crazy, but whether they are sufficiently crazy. Because I've run across a good number of crazy people, and just because somebody may at least seem a little bit crazy or maybe have a bit of an out there idea, doesn't mean it isn't worth exploring. I mean, the whole case in point in this right here is somebody presented something. I'm like, oh, this is kind of interesting. So it was interesting. It was a simple expression. How could we perhaps modify this, keeping the same core structure, basically relating the speed of light, the mass of the proton, and the proton's radius to hbar itself. And then when you happen to replace that pi over 2 with basically 1 over alpha, the fine structure constant, and we swap the proton's charge radius with its classical radius, we get about 9 significant digits accuracy to the 10 significant digits defined of hbar. So if we, let's just divide this by hbar. I think I might need to re-verify. Yeah, we're going to want to use the classical proton radius, and we're going to want to do multiplication rather than a list because I'm just listing a whole bunch of arbitrary things right here. Okay. So again, Wolfram Alpha, full disclosure, Wolfram Alpha is rounding, but at least for our initial investigation of this, when you take this expression and you divide it by the elementary unit of action, hbar, we come back with 1. If you happen to have expressions related to each other and it comes back as 1, 2 pi, 4 pi, about 1 over 137 or something, that's usually quite exciting. And that's when I kind of got excited, and that's why I basically had to do this for, again, a little bit later. I wanted to maybe get going a little bit earlier, but you know what? It's a fascinating thing. And again, this people will go around and say, oh, this is a smart dude. No, I'm literally a monkey with a magic typewriter and an idea of where to look. Why? Because, well, I'm basically just applying the method that Thad taught me, in that every once in a while, if you see something interesting, if you entertain the idea, I'm like, what if there was something to this? Why? Because maybe that would reveal something interesting. Because that's the whole thing that Thad did with at least his method for calculating the fine structure constant itself. So I'm going to go on a quick little tangent here. So, because his thing is, somebody had actually, after his book, Einstein's Intuition, somebody had reached out saying, you probably already know this, but they brought him to, I think it was either a math or physics stack exchange, where it was a Mr. DeVries. He had set up an equation that basically got about 6 significant digits of the fine structure constant. And, well, to be fair, if you have Euler's constant, which is literally listed on Wolfram Alpha, this is an approximation for alpha. And basically, as you can see, it gets that not, 0.00729737 yada. So basically, if you just do 1 over that, you're going to get 137.0360. Okay. So now this gets the fine structure constant to 5 significant digits, and it actually approximates it quite well. Why? Because 137.0360 is pretty close to the actual 1 over 137, which is 137.035999, and then we argue about the 10th significant digit there. Okay. So it's pretty dang close, but you look at it, it's like, all right. So it's 16 divided by 3 times 2/3 raised to the 3 over 4 times the 4th root of pi, pi, 4th root of 5 times pi raised to the 11 divided by 4. Okay. I don't know what that means. It happens to get it pretty well, and it's good enough that it's listed as a constant on Wolfram alpha. Okay. Thad's thing is he basically just kind of adjusted the algebra, but he has this expression over here, which is 1 over x plus x cubed divided by 2 pi, and that's all set equal to I raised to the I raised to, I'm going to put it this way. You can rewrite this in different ways. Negative pi divided by 2. Okay. So basically this was an expression that de Vries had taken the square root of these numbers before to basically just get the fine structure constant as it's generally presented today. Thad basically reworked it and made these not square roots for the x's, and that basically has what Professor Feynman may have referred to as colloquially the true fine structure constant, or its amplitude. So that's the thing that you square to get the probability of an electron absorbing or emitting a photon. Okay. So this over here, what do we get? So this, oh my God. Let me try with pro premium time. Oh God, is this expression too difficult? Wow. Wow, I guess the LLMs are overloading Wolfram alpha. It normally does this for me fairly quickly. Oh, the lag is real. Oh, hold on. Okay. Oh, this is slightly disappointing. Am I logged in? Yeah, I'm logged in. Okay, well, we'll let that calculate, and let's take a look at what questions, comments, other things that's going on. Because oh God, that's discouraging. So let's stop sharing that. That's just annoying me at this point. So if it decides to finish computing, we can go back there. Okay, so let's see what else we got. Gabriel's talking about Sandra. I feel like, did you send me an email about Sandra's stuff? Because I feel like I had looked into it before. And also, yes, I am interested in other folks that have very interesting things. Why? Okay, if there's one thing that's going to sound very corny. But one of the things that I've learned is a lot of times people are very busy. And if they're working on something and they feel like they've really got something, they found some connection with reality, well, they're going to work on their stuff. So a lot of times other folks are like, oh, look at my stuff. It's like, people don't have time because they're trying to figure things out. That's why I think that shout out to Kurt J. Mungle from the Theories of Everything channel with Kurt J. Mungle. I think that one of the reasons why he's had such success is he's exploring these other ideas. One, he is interviewing folks, but since he does have a mathematical physics background as well, he actually goes through the papers, goes through the different calculations. Like he did a 3-hour deep dive on Dr. Eric Weinstein's geometric unity. Whatever you think about that, it's when he went through that, again, I'm not going to act like I know what's going on, but as soon as he's listing like, oh, spin 7,7, it's like, I don't know exactly what that means, but I'm like, well, at least within the framework of what that's kind of laying out, you realize there's interesting things. Because one of the intersections, so to speak, of where general relativity and classical mechanics, some of the things that they have in common is, for instance, let me play the Professor Penrose clip, because this is, we're slowly building up. My old man, God rest his soul, he was an attorney. And he always told me, he's like, memes, you follow the evidence. That's one of the reasons why I ended up joining the physics monastery, because I was looking at the evidence. I'm like, all right, so Thad basically had a couple of predictions that were confirmed. I came out here like once or twice, and we were redoing some calculations with some updated numbers. And I'm like, all right, so if you predicted the muon G2 results twice, and you basically had some other, I think the classical radius of the electron or something like that, when they had the extra significant data. So I'm like, all right, well, you'd already kind of said it would be this. It's following in the error. I'm like, all right, I'm learning enough. This process seems to kind of be making sense to me. Let's do a jump. Let's invest some time as well as maybe some resources into maybe trying to get the physics monastery going to see what might be going on. But I realized that was a big tangent. The thing I was saying about looking at other people's ideas, like even Kali's given me some great ideas, and even if we might disagree upon the fundamental form, whether it's Shirley's surface, I don't care what it's called. If you want to call the HF8C Shirley's surface, by all means, I'm happy to call it Shirley's surface because we're paying homage to somebody. But maybe it is neutron decay cosmology, because I look at some of the math, I'm like, well, Thad's estimating this is about the charge radius of the neutron. I'm like, if you're going to condense a whole bunch of stuff down to about the charge radius of the neutron, I don't know. Are we going to be getting neutrons coming out? And if you got neutrons coming out, well, after about 14 and a half minutes, for some magical reason, they seem to decay into a proton, an electron, and an antineutrino. I'm like, sound like a lot of the building blocks we need. So I'm like, I'm happy to posit neutron decay cosmology because it's an idea. And since that idea and concept was in my head, I go through some of the calculations. And I'm like, dang, I think Kali's really onto something. So that's why somebody like Sandro and stuff, if they have something, and especially if you're going through it, because ultimately even Stephen Wolfram had said this at one point where he's looking, he's like, I suspect, but I don't know, that perhaps the Wolfram Physics Project string rewriting part may actually be string theory. So if you're, again, whatever you think of string theory, I'm thinking, the more and more I learn, I'm like, okay, number one, whatever you want to think of string theory, it's mathematically rigorous. So a lot of people are doing it. And if it happens to pop out a spin 2 style particle that seems to look a lot like a graviton, why wouldn't people work on it? So it's, again, I'm looking just to see what might be going on. Okay. After 5 minutes of bloviating, if you've ever watched Pirates of the Caribbean, the third movie, when they're having the Pirates Council with all the captains there, and then Jack Sparrow calls for a vote for the Pirate King, and everyone's like, why are we doing this? It's like everybody just always votes for himself. They're going around the room and everyone's voting for themselves, and then you get to Elizabeth Swan because she's a captain at that point. And she's like, Captain Swan. And I guess to Jack Sparrow, he's like, Captain Swan. And everyone's like, loses their minds. And then all of a sudden, I think at this point, was it Keith Richards or whoever's playing Jack Sparrow's father? He's like, will you not be keeping to the code? So long story short is, rather than being like, oh my God, I'm obviously right, it's like, all right, let's look at a bunch of smart people. So whether it's Thad, whether it's Rick, whoever it is, if I'm finding intriguing things, whether it's Kali, whether it's Sandro, why wouldn't I explore them? And if there are parts there that I'm like really resonate with me and I'm like, all right, this seems to be the case, I'm happy to support people and stuff, because what are we looking for? We're trying to get closer to truth. Shout out to Robert Lawrence Kuhn from Closer to Truth YouTube channel. But that's the goal. I mean, if you just want people to look at your stuff, you can just do all this clickbait and everything, but what's it going to get you? That's the thing. Does it hold water? Because if we're trying to figure out what is true, you're trying to look for minimal inputs with maximum explanatory power. If you can put in as few things as possible and explain more with less, yeah, of course I'm going to look into something like that. And again, it's for me, I don't have like the traditional background of a standard physics student. It's full disclosure, I've never finished a full physics class in my life. I get it. Took some physics in high school, did about a week and a half in college of modern physics and stuff. But when it interested me, all of a sudden I went from like, math is too confusing, to all of a sudden, I can calculate the mass energy of like a proton going 0.99999 times the speed of light. Why? Because it was interesting, and then calculus had a reason, and then it made sense to me. So again, I stand by, I think I call it universal truth number 4. Again, just a parable, if you would. We never know where a good idea may come from. And that's why, especially if you have something that you haven't really seen before, like I've had, Bill Manuel on here before. And as far as I can see, he found a very interesting relationship between the surface area of a black hole and Landauer's principle. And I did a quick search, and there appears to be a 1 over log 4 relationship, which is in some of the equations there, but I hadn't seen anybody really express it and highlight it like he has. Again, that was just a basic cursory search, so I'm like, all right, let me explain this. And he's sharing things with me, and I'm sharing things with him. And if we have the ability to, because I'm just one dude, we're just all people. It's like, I feel like we're stronger together because, well, I don't know everything. Nobody knows everything. Even ChatGPT, I mean, it tries to read the whole internet, but it can only work with what it's got and as we're prompting it as well. Now, it's a very useful tool, in my opinion, but you have to be careful with tools that we're not necessarily using them as crutches. Because, like, for instance, like a GPS, very often, great at getting you 99% of the way there. And then sometimes it's like, it's not quite accurate, so you drive by and everything. So I'm happy to look at different things because, well, number one, that's how I learn. Because there's so much I don't know. Okay, sorry, I've been ignoring the chat and rambling on. So let's finish with what other folks are saying. Okay. Kali's saying, did I look at the Dirac neutron? It has the electron in the same orbit as the positive charge, but charges separated by the fine, even when they No. Send me that, please. I'd love to look at that. That would be fascinating. Because I mean, who among us hasn't been like, wait a second. So when a neutron decays, it's like, all right, we're getting a proton, an electron, an anti-neutrino. You're just like, well, isn't that just all what it is, like pushed together? And people are like, no. But then it's like, oh, once you start getting to a neutron star, it's like, oh, those electrons kind of go into the protons and then they become neutrons. You're like, what? And again, I'm not a cosmologist or a condensed matter physicist. I could be butchering that. This is my general zeroth level knowledge about what's going on. So, Poindexter is commenting, the cosmos is open sauce. I'm going to conjecture that the cosmos is awesome sauce. Oh, no, I'm not going to share. No sharing passwords. Yep, no, we got to be guided by experiment. Oh, thank you for reminding me. If you couldn't tell, I'm kind of ADD. I jump around a lot. But the interesting thing is the area where general relativity and quantum mechanics, there's two interesting things that I think are worth noting. Number one, let me, actually, speaking of Robert Lawrence Kuhn, this was from, I think, about 15 years ago. Let's see, Penrose. That's the key word that I need. All right, so let me present. We'll get a share the tab. All right. So here we go. Professor Penrose on Newton and Einstein's precision of gravity. So I'm going to take a look at this.
Now, mathematics can also describe things in the ordinary physical world, gravitational attraction, electromagnetic attraction, and with the same kind of descriptive accuracy?
Well, there's another, even more in a certain sense. Newton's theory already had a precision of something like 1 part in 10 to the 7, so that's 10 million.
Wow.
And then Einstein comes along and produces a theory which is now known to have a precision something like 10 to the power 14.
So what does that now begin to tell us about what mathematics really is?
Yes, well, in a sense, this is telling us that our picture of physical reality depends on something, in a sense, which is more precise, at least in our understanding of it, than how we think about the world. It has its own life, in a sense.
Okay. So I remember Thad had mentioned something about that. He thought it was originally Professor Brian Greene that had said it, but then he eventually found it was Professor Penrose that had said that. Okay. So just noting that, all right. So basically the Newtonian gravitational constant has a precision of about 10 to the 7. Okay. And then Einstein came along and gave us a precision of about 10 to the 14. Okay. So for those of us that have delved a little bit into some of the history of physics and everything, it was, I believe, Lord Kelvin who was at least attributed with having said that basically physics as we know it is basically complete. It's only a matter of measuring the precision of the 6th significant digit. Okay. So that seemed to be true. And then once we got to the 7th significant digit, things really started to get weird and everything. And then ultimately, we ended up having to develop quantum mechanics, which then, at least according to CODATA, the most precise measurement, I believe it's the anomalous moment of the electron, is measured at 14 significant digits. So wait, hold on. So if Newtonian gravitational constant, big G, has a maximum precision of about 7 decimal places, and then once we reached the 7th decimal place, we needed quantum mechanics, and then general relativity has a precision of about 10 to the 14, and as far as we know from our best measurements, we have measured precision of 10 to the 14. Gets the old noggin a jogging. So I'm also very biased about that because the way that had basically broken it up, he's basically also utilizing the whole binomial theorem. So again, I think that's also, was that Newton? Hold on, I need proper attribution. Binomial theorem. Binomial theorem. Where did it come from? Oh God. Elementary algebra. Okay, maybe that's just algebra. Who invented? Oh, of course it was Newton. Of course, the generalized binomial theorem, which applies to any real exponent, is attributed to Isaac Newton. I feel like Jerry Seinfeld. It's like Newton. So, but basically, that is utilizing the binomial theorem to basically get about the first 7-ish significant digits, and then seeing if we can piece together and fill in the puzzle pieces to extend for the rest of the measurements there. Okay. Oh, that's interesting. Is it about 14 minutes for the decay of a neutron on Earth? Okay, so if it's going close to the speed of light, it's going to take longer. Okay, so that kind of makes sense to me. That is interesting. Maybe... Too bad. Here's the thing. I'm kind of agnostic on the graviton. Do I necessarily know that that's a thing? I don't know. And again, why would I hate on somebody that's doing something that they're trying to push science forward? I don't know. I think the rising tide lifts all boats. That's my general take there. All right, Callie, you take care. Have fun talking to Shirley. You take care now. All right. Let's see. Poindexter's commenting closer to the truth in an interesting episode about power laws and their ubiquity in different aspects of science, including bio. Okay, I don't know. Maybe I'm just I stay away from a lot of the biological stuff because it's like, I don't know. Maybe also when we talk about certain biological things, I also maybe get a little queasy. I don't know. It's a personal flaw. Let's see. Experimental support. Well, that's the thing. Ultimately, if you can have predictions, like if you have experiments and all of a sudden it seems to run in line with your predictions, that's pretty cool. Well, mathematics does seem very unreasonably effective for actually being able to make predictions and actually model our world. So whether you're driving a car and you're going, I don't know, 60 miles per hour or 100 kilometers per hour, it's like, all right, you have a speed, and then you're dividing it by a unit of time, so you're going to get your speed there. If you happen to take the Planck length and you divide by the Planck time, you're getting basically the speed of light. I say basically because there's a slight caveat there. Because again, we know the speed of light, it is literally defined at 9 significant digits. If that's defined at 9 significant digits and hbar is defined at 10 significant digits, and we have these high precision measurements to 10 significant digits, why do we only know the Planck length and time to 5? We have them to 7, but the error in those last 2 digits can be kind of big-ish for very small things. So that's another thing, that maybe there's something around, at least given our system, the 7th significant digit of precision. Maybe quote unquote Lord Kelvin's foible, if you want to call it that, is actually pointing out something very interesting. Because I mean, if Einstein's going to say, it's like, oh, my biggest blunder was I included the cosmological constant and I shouldn't have. And then lo and behold, it's like, oh, there appears to be some cosmological constant. Now, is the cosmological constant constant? I don't know. I can come up with a cool expression that seems to fit the CMB calculation for it pretty well. Would I love that to be correct? Sure. Doesn't mean it is, because if it is changing, perhaps there is some rotation going on. Again, I am very biased because at least at the Mysticon, at the upcoming conference in Portugal, I'm going to be presenting a model that seems to be including some rotation there. Let's see. Gabriel's commenting. There's a before and an afternoon, just like there's a before and after Weight Watchers, but for real. Oh, that's funny. But no, you kind of look to experiments and stuff, and maybe, who knows, if I happen to go on one of the other Demystify Psi paradigm drifts and everything, I probably should have done it rather than trying to, here's a method to calculate the cosmological constant. Yeah, I probably shouldn't have done that with a 1-minute pitch. That was not sufficient. I should have just followed up with, because if you're looking at experiments and everything, it's okay, we got to connect things to reality. That's one of the things Professor Feynman really stressed. Now, some may say it's like, well, if it doesn't agree with experiment, it's wrong. Well, I mean, if it's a high precision, accurate experiment, maybe you need to go back to the drawing board. Occasionally, some experiments, sometimes there's an error. Somebody maybe messes up or something. It's kind of like, oh my God, it looks like maybe neutrinos go faster than the speed of light. Or maybe an Ethernet cable wasn't plugged in quite all the way, so maybe there's some interference, so you don't know. But again, we can kind of wrap up. Oh, let's see. But what do we have here? Okay. So let's go back over here. So what I probably should have done, or then maybe next time I go on Paradigm Drift, we'll take a look over here. Because, what was it? We had our little, so if you take the root of action, what the heck is that? What we're doing is literally naively, and this is thanks to Eugene the philosopher. Shout out to him for the Eugene notation. Dad may have put this up on the board, but I didn't really retain it if it was even there until Eugene had pointed it out. So I call it the Eugene notation because, well, we should give credit where credit's due. We take the elementary unit of action, Planck's reduced constant hbar, and we divide it by the reference of action, which is the joule second, given our coherent system of units, aka force equals mass times acceleration, energy equals force times distance, and power equals energy divided by time. We then have a coherent set of units. Cool. So if we do this, we're going to get, it's about, I don't know, like 10, about 10 to the minus 17. That doesn't mean a thing to me. However, if the question of why does the Higgs boson have the mass it does rather than being at the Planck mass scale, well, if we multiply the root of action by the Planck mass, we get an interesting number. Okay. You get 125.38 giga electron volts. And again, there's a little bit of rounding in there. So that's approximately equal to the Higgs boson mass. And again, it's fairly uncontroversial as far as we know, at least for measuring what we call the Higgs. It's about 125 GeV. Okay. So what ends up happening is if we go to Higgs boson mass, okay, let's go to, we go to CMS. Hold on. the CMS collaboration, which recently was awarded the Breakthrough Prize. Let's go to, I think this is the old one. We need to go back to the CMS right there. CMS collaboration. Okay. Oh God. Hold on. Okay, that was the old measurement. Where are we at? Recent. Let's just go to the generic one. All right, public results. Here we go. All right, most current data. I think it was on April 10th, I believe. Or maybe the 16th. Where was this? 24th. I think it was... Okay, hold on. I'm sorry, navigating those websites is a pain in the butt sometimes if you're not familiar, so we'll just go to... I just searched my YouTube channel because that's where I put a lot of the links. Okay. Where is this? Educated guess, blah, blah, blah. Oh, that was a while ago. Hold on. Another word. CERN. See? Back in the days of trolling Professor Keating and Professor Wolfram. Okay, here we go. So let's go here. All right. So the CMS collaboration results. I know, a very circuitous route. All right. So this was from, okay, so from April 11th of this year, the CMS collaboration. Okay, the combined measurements, standard expectation of, they're estimating the Higgs boson mass at 125.38 gigaelectron volts. That seems familiar. Where have I seen that number for? 125.38 GeV. Huh. 125.38 GeV. How very interesting. To be fair, there's actually 125.376 GeV with a standard deviation or error of 2 with that 6 in the last digit there. That's the uncertainty in the Planck mass. So, yes, I would tend to agree that experiment is very interesting. So maybe next Paradigm Drift I'll actually talk about this again. But again, it's one of those things that's cool, but maybe instead of... Listen, I occasionally use the quote theory of everything in quotes because ultimately if you're trying to explain everything, that seems very hard. So how about, at least as Professor Wolfram posits, a fundamental theory of physics? Okay. That's basically what I'm looking for. And then rather than trying to do all that stuff at once, it's like, yeah, let's just look at a couple of things. Because if there's a thing called the hierarchy problem, which technically now involves why the Higgs boson mass is a lot smaller, I don't know. Maybe it's because it's the Planck mass times the root of action. Conjecture. We'll see what happens. So that's about all I got. So let's see. I think that's about all for right now. So hey, thank you all for joining, and for those that may join temporally in the future, it's a heck of a time. So here's to a better tomorrow. But other than that, peace out, everybody. Catch you later.